Cherenkov radiation. The Russian physicist P.H. Cherenkov discovered that a charged particle traveling in a solid with a speed exceeding the speed of light in that material radiates electromagnetic radiation. This is analogous to the sonic boom produced by an aircraft moving faster than the speed of sound in air. Cherenkov shared the 1958 Nobel Prize for this discovery. What is the minimum kinetic energy in electron volts that an electron must have while traveling inside a slab of crown glass, index of refraction 1.52, in order to create this Cherenkov radiation? Okay, now we have to remember the relativistic kinetic energy. What is the relativistic kinetic energy? It is the relativistic correction factor gamma minus 1 mc squared, mass times the speed of light squared. Now the electron charge is 1.6 10 to minus 19 coulombs. The index of refraction in the material is 1.52. The rest mass of an electron is 9.11 times 10 to minus 31 kilograms. Okay, so in crown glass, where we have index of refraction n, the wavelength in air is reduced to lambda divided by n, and the speed of light, c, is reduced to c divided by n. So that's the speed of light inside the material. And the relativistic correction factor gamma is 1 minus v square over c square to the power minus 1 over 2. Now you can see that v over c is equal to 1 over n from this equation. So in vacuum we have c is equal to lambda times the frequency. The frequency of the light is determined by the source. Therefore, the frequency doesn't change when light enters this material. What changes is the wavelength, and that's going to correspond to a change in the speed of light in the material. So the frequency is constant. So we have v is equal to lambda prime times f inside the material. So where lambda prime is lambda divided by n. So we can substitute for v over c 1 over n. So this gives us, for the relativistic correction factor, 1 minus 1 over n squared to the power minus 1 over 2. So with that, our relativistic kinetic energy is going to become gamma minus 1, so which is 1 minus 1 over n squared to the power minus 1 half minus 1, that's gamma minus 1, mc squared, mass of the electron times the speed of light squared. So this is going to give the energy in joules. We have to divide it by the electron charge in order to get the relativistic kinetic energy in electron volts. Okay. And we know that the speed of the charged particle, which is the electron in this case, has to be greater than or equal to the speed of light in that material. So V, the smallest V we can have for Cherenkov radiation is C over m. So that's basically what we have substituted into the relativistic kinetic energy expression. Okay, so if we plug in the numbers, the relativistic kinetic energy is 1 minus 1 over 1.52 squared to the power minus 1 over 2 minus 1, that's gamma minus 1. And then we have mc squared, 9.11 10 to minus 31 kilograms times 3 times 10 to 8 meters per second speed of light squared in vacuum. And we have the electron charge 1.6 times 10 to minus 19 coulombs. And this gives us a relativistic kinetic energy of 168 kilo electron volts. Okay, so the emitted Cherenkov radiation by the electron traveling in a slab of crown glass has a propagation speed of c divided by n. That's the speed of light in the material. So the electromagnetic waves emitted by the electron traveling with a speed faster than the speed of light in the material is going to create this Cherenkov radiation that's going to propagate in this crown glass with the speed c over m. Okay, so let's see what we did here. We are talking about Cherenkov radiation, which was discovered by this Russian physicist P.A. Čerenkov, and that's allowed him to get the 1958 Nobel Prize for this discovery. And what Čerenkov says is that if you have a charged particle in a solid that's propagating with a speed exceeding the speed of light in that material, it will radiate electromagnetic radiation. And at the end of the solution, I've also said that this electromagnetic radiation, electromagnetic waves in that material will travel with the speed of light in that material. Okay, so what is the minimum kinetic energy in electron volts? If we're looking at the minimum kinetic energy, the minimum speed of the charged particle should be the speed of light in the material. So that it's going to create the Cherenkov radiation. Now the material has an index of refraction 1.52. The relativistic kinetic energy is gamma minus 1 mc squared. We're using relativistic kinetic energy because the speed is close to the speed of light in vacuum. And the relativistic correction factor gamma is 1 minus v squared over c squared to the power minus 1/2. And we recall that when electromagnetic waves enter a medium, the wavelength is reduced by a factor index of refraction, and the speed is reduced by a factor index of refraction. The frequency doesn't change. So v over c is 1 over n, that we can substitute into the relativistic correction factor expression, and putting this into the relativistic kinetic energy equation, and also noting that the energy that I will obtain in joules must be divided by the electron charge in order to convert to electron volts. We obtain this final expression, and plugging in the numbers, we obtain 168 kilo electron volts. So this is the minimum kinetic energy an electron must have inside crown glass in order to emit Cherenkov radiation, which will propagate inside the crown glass with a speed c over n.